So, welcome back. So we so far had seen three kind of topics, no, in the theory lectures and in the tutoring. So we saw neutrino oscillations. Then yesterday we looked at neutrino mass generation from these seesaw mechanisms, and now suddenly we remind ourselves of the title of the school, which is neutrino stellar beta decay. So today's exercises are about that. And actually, we'll skip the first one because we did it yesterday without knowing in class. Okay, so the first was to argue why this quantity m beta beta appears in in the rate of neutrino stellar beta decay. It actually appears squared in the rate because it appears linearly in the amplitude. And Claudia shown you with, I will not repeat what Claudia did, but she has shown you that in the diagram, this is the standard contribution to neutrino stellar beta decay. If you are just very conservative, let's say you say, I only have the standard model and okay, I know neutrinos have mass. Then you expect this to be there. This is the standard contribution that you saw hundreds of times by now. Where you sum over all these massive neutrinos, and you saw with Claudia that the projectors make it so that everything is proportional to the masses. So this amplitude will be like masses of each neutrino k. And the important thing here that is very different from other processes is that this violation of lepton number is giving you twice this u e kappa, twice meaning it's squared. Okay, so this is just to make it very clear that this is why you can see the Majorana phases here, but not anywhere else. There is no conjugate, there is no absolute value. It is the square of the matrix element, so it is not blind to the eta 1 and eta 2. And if you put in here, so this is the m beta beta, if I put an absolute value, and if you put in the PDG parameterization, is it clear that you get that? So what can you tell me about this expression? What comes in here? Or what do you notice doesn't come in? To get here, I just put here the explicit form of the 3×3. Okay, what is missing here? In the sense, I mean, this is correct. It's not that it's wrong, but there is a parameter which does not appear here. Theta 2, 3, because we're just looking at the first row of the PMNS. Okay. So, okay, this we did yesterday, why it happens like that. Now, the goal here would be, theoretically, to let's do this plot together, but since we don't have so much time, realistically, we will discuss how to get it, which is already non-trivial, and we will use data from the new fit collaboration that Claudia cited several times. So you see I don't know how many of you have, once in your life, reproduced this plot that people show, no, this plot, you reproduce it, but I think, are you the only one? Okay, the theoreticians reproduce it because they don't care about the important stuff. This is the nice part of the decay rates, because as we saw this morning, it's really hard to the bottleneck is basically the nuclear matrix elements. But let's try together to understand how you would go home and produce the nice plot. So the fits values, I'm just going to flash them here. New fit collaboration will give you a global fit of all neutrino data, will give you some ranges for the angles. We don't care, as you said, we don't care about theta 2, 3 for this. They're very precisely determined. We don't know at all delta, so 3 sigma range for delta is extremely large today. but we know all the rest very well. Now, together, I mean, this is the formula. What would you do? Let's start with normal ordering. How would we write this in terms of observable parameters? I mean, I know a theta 1, 2 is already an observable parameter, so I just keep this. The Mariner phase is not yet known, of course, but I keep it as well. Now, do we know M1? Exactly. We know the mass square difference, but we don't know M1, right? So this is our variable. This is the x-axis, as you've seen in all these plots. I will call it M light, because it's the lightest. And that's it for this first term. Then there is the second term. So I'm really thinking, how can I put this in a computer? What I will do in the end, I mean, and eta 1, eta 2, I will vary them in 0 and pi because they are really unknown. The rest I either fit to the best fit values, or if you want, go back to this table. And you say, I will vary theta 1, 3 in the 3 sigma range here, or theta 1, 2 in the 3 sigma range to see how really these areas in the plot, the allowed areas, are wide. But okay, for a first approximation, you could just do with best fit values. Now, M2. How would you write it, following your suggestion? Yes, so to go to the mass square differences, M2 squared, but we don't know M2 squared, we know delta M squared to 1, right? Which is the difference of squares. Then we need to sum M1 square, which I'm calling M lightest in NO. Okay. And finally, yeah, so for normal ordering, it's really, really direct because usually people, if you also look at the fit, for normal ordering, people give you 3, 1. There is a legend that I cut, but this is 3, 1. For inverted ordering, they give you the absolute value of 3, 2. So you have to be careful with this, but here it's really the same. Okay? Now, mathematically, what is this quantity? This is that same expression. What is this? How can you see this quantity? I mean, these are complex numbers, right? This is the absolute value, so the magnitude of a complex number, which you get from summing 3 complex numbers. If you want, I mean, everything is really except the phases eta 1, eta 2, and delta. So you are summing 3 vectors of size. The first size is this one, cosine 1, 2 squared, basically. Cosine 1, 3 squared is approximately 1, ml. The second vector has this size, and the third has this size, and you see that the sizes of these vectors depend on the lightest mass, because if the lightest mass is very small, then this guy here is basically a complex number which has a very small magnitude. And whereas if it's very large, then this and this and this are dominated by ml, and these vectors can be comparable. Then you just need to look at the other things. So the computer will do this for you. But it's nice to have an understanding of that these are 3 vectors, so 3 arrows in complex space, and you are summing them, so you are putting the arrows back to back. And the resulting sum, so the resulting arrow, this is its magnitude. Okay? Now, let's do the same for I/O. What do we get? Please. in a moment. So you think, okay, we can do this. What do we do for delta? That's a very nice question. Does it matter? Who thinks that delta matters here? And who thinks delta does not matter? And who doesn't know? You don't know, so the rest don't care. Yes, common phase. This is the key word. So since this is an absolute value, you can multiply everything inside the absolute value by a phase because the magnitude of the vector doesn't change. So you can multiply everything by exponential of 2I delta. This means that it will appear here and here, but since you don't know the Mariner phases, we can define eta 1, 2 tilde or prime, okay, which is eta 1 or 2 plus delta. This is what happens when you multiply everything inside by the phase with delta. It drops out here, and then this and this become eta prime. But since this is unknown, varies between 0 and pi, it doesn't matter what this is. Okay. This will always be taken mod pi, so essentially, even if we knew delta to a very high precision, it doesn't matter. This is what Claudia was saying, okay, yesterday, that there are two Majorana phases essentially, and in some parameterization it's more direct to see it than in others. And the Majorana phase, you can say they are this, so they are completely, the Dirac phase plays no role. Okay, so this is what you tell the computer. You don't give the computer the 3 sigma range for delta, just for the angles and the delta m squares, right? Now, what about I/O? Oh, any more questions about NO? Feel free to stop me, okay? I/O, what do we get? The angles we don't touch, no? Let me already put here our nice conclusion that we can get rid of delta. So for I/O, how do I make experimental accessible quantities appear? So how do you recall how it is I/O? So NO is like this, 1, 2, 3. I/O is like that. So yeah, third term. But you're right that the key point is also that it's no longer this term, the lightest one. M3 is the lightest one in I/O, and we put it here. Okay, now the ML is different. And okay, a bit of algebra. I mean, delta m square 3, 1 and 2, 1. Now if you use delta m square 3, 2, it's a bit more complicated. So delta m square 3, 2 is negative because it's inverted. So you take the absolute value, you sum ml squared to get the m2 in this term here. M2 squared that you square root. So it would be something like this, okay? This is the lightest one. This is positive, which is minus this, but this is negative itself, so we can just think like that. Did a lot of steps in sequence, but I hope it's clear that there is no magic going on here. And even a bit worse for this one, which you see, you need to involve both mass square differences if you want to be very precise, but in the end, this will dominate. Nevertheless, I mean, you need to have this and this, that second cancels here, so that you get 3, 1, and then with 3 you get M1. And now you have all the tools. By the way, let me also flash what we concluded. Delta will cancel out effectively. And we have all the tools to do this plot. So now you'll tell me, I'm a computer, and you tell me what should I do precisely. even if I fix all the angles and let them square to best fit values, I still have some freedom, no? In the Majorana phases. They go from 0 to pi. So what can I do? Exactly. This is the first approach, very, let's say, fast and dirty approach. You just throw points. So you say, I select some values randomly, and then I compute them beta beta in both cases, and you should get something like this. Okay. So this is the very, let's say, you don't want to waste time. This is even varying the angles and the mass square differences in the 3 sigma ranges, but okay. If you don't vary them in the 3 sigma ranges, maybe you get something a bit strange, which is very narrow here. So don't get worried about that. No, this is by varying everything. Everything. If you just vary the phases, actually, you would get something a bit narrower. So if you try to do this in first approximation, just to play with it, don't be scared if it gives you something which is very thin. You get it thick like this because you vary also the angles and the mass square differences. So essentially, it's just throwing numbers into here. There are no unknowns. Okay, the Majorana phases are also being thrown in, and you get something like this. What if we want to refine it? Because maybe to present this in a paper is a bit ugly. Yes, but if you look here, what is happening here? This border is much smoother than this one. This is just a statistical artifact because to get here to low values, you need cancellations to happen somehow. So from a simple uniform distribution throwing numbers, you will get a lot of points here and not many here. So even if you interpolate, this is a very rough estimate. Okay. So what people usually do is they discretize something like ML. Okay. It's not. You see that there is. You can try. I don't expect it to make a difference in the sense that it's not that you have very in the variations very large differences. You have some differences between the scales, of course, but they are already in around the right magnitudes. So it's not that now you vary them logarithmically around their best fit values, and this one varies linearly. It's really a matter of cancellation of vectors which are large and of comparable orders of magnitude. But you can try that. So you should get something very similar with enough statistics. So what people can do is just say, I fix a value of ml, and then I numerically maximize and minimize this quantity, which will give you, let's say, the value here for NO, and for the same ml and IO, I try to maximize and minimize this quantity here. And this is the second numerical approach. We will go to analytics in a second, but the numerical approach will give you something smoother like this. This was done in Mathematica, just using n maximize and n minimize, okay? You mean okay, so I cheated a bit. I kept more statistics below a certain value. So it looks kind of uniform. If you don't, you get something which is less populated here, or you have too many points that the Mathematica crashes because you you get a good result in this region, but here you have a number of points which you don't need. So really, I think to get a contour, you really have to understand what is this maximum and what is this minimum. And we can even do it analytically. Yes, I think I used a very small step. I think it was a logarithmic discretization, just so I could use like 100 points overall. Exactly. And this is indeed what you need to get this. For instance, here I had to add some points because this feature was not getting correctly resolved. If you do numerical methods, of course, and you show me 10 to the minus 7, this will not be 0. This will be some jagged thing here that has to do with convergence problems. So if you get something, some numerical artifact like this, also don't worry, it's normal. But we should understand why we get a cancellation in one case and not in the other. Okay. For instance, in I/O, if you see the magnitude of these vectors, actually let's start a bit let's start with NO, and then we go to I/O. What are the magnitudes of these vectors? For instance, for large M1, you have some picture like this. So large M1 means we are in the right-hand side of this picture. The thing is the masses are quasi-degenerate. And you get that the biggest one is this one with the cosine of 1, 2. Then followed by the one which is sine of 1, 2. Oh, sorry. And this is the result of summing them, no? So, okay. It's a connection problem. And the third one is the smallest one, and they are oriented given by just the phases. So actually here, forget it, I put a minus sign here. This arrow should be like that, okay? To give you a concrete example. So the angle that it does with the x-axis, the real axis, is the phase eta 1 or eta 2 prime. Okay, this is the angles that these vectors do, and you are summing them, so you are putting them back to back, and you are interested in the absolute value of this sum. The sum is this guy here, and you see that for large M1 this is large. When can we try to, how can we minimize this M beta beta? Just by looking at the arrows. Yes, we have freedom to change the angles because we don't know the Mariner phases. Yeah, so let's say the modulus are fixed because we fixed M1 and the angles and so on. Varying the Mariner phases, you see that, as you are saying, if they cancel, or we try to make them cancel, you can get something like this. But if one vector is much larger or larger than the sum of the other two, you will not get a cancellation, no matter how hard you try varying these angles. Okay? So the detailed analysis, you can find it in papers. If we're not going to do this here, you can understand this feature just by saying, can I cancel the sum of three vectors? Can I not cancel it? If it's large M1, you cannot cancel it, and this is why in the plot this is bounded from below to the right. What if I want to maximize it? Yeah, so here maximization is much clearer. No, it's just that if I want to maximize this, also for I/O, this should be plus 1, plus 1, plus 1. All the vectors should be aligned, and this is the how far I can stretch this M beta beta. If I want to minimize, it may depend on the region. For instance, if you have large M1, you may need this kind of cancellation where the big one is this, and then you have to do something like this. But here by convention, we didn't put delta, so let me say like this. This is a way to minimize NO in the large M1 region. Essentially, these two vectors are summing to try to cancel as much as possible the first one, which is the largest, but they cannot get there. In the small M1 region, things are a bit different. No, yeah, I'm just going into the extreme. Now it's the far left. Before it was the far right. You see, for the very small m1, this first vector, since it's proportional to ml or m1, it's going to be very small. And the dominant one will be the second one. And here again in this limit, you cannot, you sum them to find it and you cannot make it vanish. Okay? You see this visually, but you can see it numerically. And what is this value mean to the left? So this was for the right, for the very large ml. To the left, small ml. Which sign should I put here? Sorry, small ml. So in the plot, I mean to the left, I mean very small ml. And to the right, which was the thing we analyzed first, I mean large ml. This is the situation for small ml. So if I want to maximize again, I just sum everything with plus. But if I want to minimize, what are the signs I should do? I should use? Which is the largest vector? So this one is the largest one. And we try to cancel it with both of these. Is that correct? However, since we are using the convention where we absorb this sign, let me flip all the signs. So you see that to have a maximum, the Mariner phases need to give you +1s. To get a minimum, some of them have to give you a -1. Which are the values of the Mariner phases that give you these? This is the question actually. Which values of the Mariner phases give you the boundaries? Almost, because what we have there, we have exponential of 2y psi. Yeah. So certain combinations of these. In fact, to be more explicit, I'd have the figure here. So if you have plus plus or you have the maxima always, minus plus you get the minima here and for IO and here for NO. But for this region, as we saw, the signs have to be different to get the minimization. It's plus minus instead of minus plus. And as you were saying, this is these phases, eta prime, being 0 pi over 2. It turns out that these values of the CP phases are actually special because they are CP conserving values of the Mariner phases. This is not so easy to see. So for the Dirac phase, it's very clear because it's either 0 or pi and then your PMNS is real. No difference between neutrinos and antineutrinos, which you got from conjugating. But for the Mariner phases, it's a bit trickier. But one can prove, okay, that there is an appropriate transformation which we can call CP if the phase is pi over 2. So meaning that there is a factor of I in the PMNS, right? The PMNS is as to the right the Mariner phase, exponential of I etas, and exponential of I pi over 2 will give you a factor of I in the rightmost phase matrix. But this is still CP conserving. Okay, this is a non-trivial thing. Now, yeah. Yeah, so it's a kind of way to disentangle Dirac and Majorana. It's a way to parameterize so that Dirac only appears in oscillations and eta primes only appear in Majorana, no contamination. These are the true, if you want, these are the true Majorana phases. Because you removed an accidental dependence on delta that was there because of the parameterization. Another way to say it is, I measure eta w- 1 prime and eta 2 prime. Well, or maybe I measure this sum. I have some constraint on these guys because I have a constraint somehow on the differences of the phases. But I will not have a constraint on the global phase, so this will not give me anything on delta. Yes. Yes, delta. And you cannot say anything about delta from here. Yeah. Yes, to have full CP conservation, you need to have these guys with the primes equal 0 or pi over 2 and delta b 0 or pi. Yeah, yeah. No, you're right. If delta is not 0 or pi, even if these are these values, CP is broken. And yeah. But you should, either parameterization you choose, the physics should make sense. Yes, this is, yes. And this is an important point because people will sometimes try to tell you CP violated here but not here. And to be precise and consistent, CP should be defined over the whole Lagrangian. Okay, so sometimes people say, oh, CP violation comes only from this part, but things get infected via loops and so on. This is to say that CP conservation, you constrain all the phases at the same time. If one of them is not one of these special values, CP is violated, end of story. Except maybe you see it in one process and not the other. Yes, 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 exactly. Exactly. Okay, so to continue, I mean, if you wanted to solve these equations, sorry, if you wanted to really find these borders, you would need to solve the equations to minimize. But if you have these signs, you can do this much easier because then you fix the signs and you will find these lines. Now, what about this region here? When do we have a full cancellation? It turns out that for inverted ordering, you cannot get it because one of the vectors will always be much larger than the sum of the other two for any value of M3. So you can never go below this threshold in inverted ordering. This is why people say, okay, the next generation of experiments will completely cover the inverted ordering region. But for normal ordering, we could have this well here where we fall down and the rate is very suppressed. Okay, how would you go about computing this range here? The range of M1, which actually leads to vanishing M beta beta. You have to program this. Mm-hmm. Wait a moment. So exactly this equation we should look at, but I want it to vanish. So you are effectively solving. I think you are solving in your head this, no? Yeah. So this will make you have some correlations numerically with, and you will find ML which gives you this. If you use the best fit values of the angles, I mean, here you no longer have the uncertainty of the phases because you have fixed the signs because you are in this border. This is small ML. And there will be a point here. And from this point onward, you can get cancellation because there the vector lengths will allow you to cancel things. So you will get something like 3 vectors which you can completely close and cancel the m beta beta signal. As you are saying, we have to solve this equation. So you will find ml. If you vary, if you do it on the left side, so small ml, it's this with plus and minus. Here m tilde are just these, I'm calling all this m tilde 1, m tilde 2, m tilde 3 are the sizes of the vectors. And if you are interested in finding the constraint from this side, you just use the other signs, minus, plus, and you set it to 0. So this way you can find, for best fit values, the upper side gives you this number, the lower side gives you this number, okay? And if you vary a bit the angles and the phases, sorry, the angles and the mass square differences, you should get a bit wider range, which matches the plot. So no signal in m beta beta is possible if neutrinos are normal ordered. And it would happen, could happen, if it happens, it would be in this range of m1. And this leads us to the last question of this part, the first part, which is, what do you think now, in view of this result? Assume then the experiment finds no signal. Can we at some point say, okay, neutrinos are Dirac particles, let's go home? This I put to your vote. So no neutrinos double beta decay. I give you a bit to think about it. So who thinks we can not conclude this? Who thinks we can instead say, yes, we find no signals, so they are Dirac particles? Okay, so, and who doesn't know? Okay, and the rest don't care. So, indeed, you're right. Why? Why can we not say the neutrinos are Dirac particles? But let's say you have a very good experiment, really. So, but they are still Marana particles, even if you don't have m beta beta. So, yeah. So, are they Dirac or Marana? Can you answer this? If you don't see any signal. But wait. In right, you could never find, as we saw, the Marana phases canceling the probabilities. Yeah. So neutrino oscillations will never tell us this, if it's Dirac or Marana. Also because in neutrino oscillation experiments, neutrinos are ultra-relativistic, which means that any effect distinguishing Dirac and Marana would be proportional. I mean, if neutrinos are massless, this question doesn't exist. Are they Marana, are they Dirac? They are nothing, they have no mass. If they have a mass, all effects are suppressed by these kind of factors. So neutrino oscillations, this is absurdly tiny. You will never see any effects in neutrino oscillations. Maybe you also don't see effects in neutrino stellar beta decay. And you are telling me you cannot conclude anything from this. And you are correct. Because if you see, it's the opposite, no? If you see neutrino stellar beta decay, you know neutrinos are Majorana. Which is saying non-Dirac. So it's not an equivalence. And the logic is, if neutrinos are Dirac, which is equal to non-Majorana, negates this part, you will not see neutrino stable beta decay. Okay. So is this clear? Okay. So it would be very, very cruel of nature to put us in this region with the phases that cancel it, but let's, yeah. Yes. Yeah, that's the question. How can you tell if neutrinos are Dirac? Not just here, you will never be able to. Yes. Only God knows, let's say. Yes. This is something we can never know for sure. But even if you find 5 other processes, okay, that can tell you whether it's Maran or not, it should be something like this, where if it's just slightly Maran, in the sense that the source of lepton number breaking is small, you can be in a region of cancellation of this observable. For instance, here we are assuming, okay, standard neutrino exchange. So you tell me, but IO will never have this problem. But who tells you that the standard model is just standard model neutrino masses and that's it? Who tells you nature is this? It We have observed, but then there could be other processes, like Claudio was telling you, that mediate neutrino stable beta decay, and the interference they can interfere because it's the sum of the amplitudes, not the sum of modulus square. And in fact, we will see this in the next exercise, which I only show a bit the solution and discuss with you, is if we add, for instance, a sterile neutrino to the picture, okay? Standard model plus 3 massive neutrinos, but plus a standard sterile neutrino. Here, how do things change? If it's light enough, how do you expect m beta beta to change? I mean, theoretically, from the formula, I'm not, I call it U, E4. No, theoretically, if it's light, you can reproduce the same derivation as you did before using the diagram. So what happens is you will have an extra term here with some new mixing angle, or let's say the element UE4 squared with its own Majorana phase, let's call it theta 3, times the mass of the sterile neutrino, I call M4. Right, so if it's light enough, we recover, thank you for this, we should recover the standard. In fact, let me show you some plots. So this is exactly what happens, we just add a term. As Matteo was saying, this mixing could be very small, could be very large. This M4, we also don't know, as you are saying, it can be very small. So, sorry? Yes, because it is a sterile neutrino, meaning it will not couple to the Z boson. No, it's you don't add a fourth lepton doublet which has gauge interactions. You add, let's say, gauge singlet, like we did for the type 1 seesaw. But now instead of putting it to 10 to the 10 GeV, you put it like EV scale. Right-handed or left-handed, it doesn't matter really because there's just one chirality. It's like you add a new 4 which can have, you can put it left-handed, but then you build things with it and it's right-handed new 4 LC, which is right-handed. It's a Majorana guy. So this is actually an important point. It's convention. Sometimes you get confused. Are we adding right-handed neutrinos, left-handed neutrinos? We're adding one Weyl spinner, which is half a Dirac spinner. It's the minimal amount of fermion you can add. And it is one chirality. And the whole point is you can take this, apply the C, and you get this is right-handed. This PL on this is 0 because it's completely right-handed if this is left-handed. Just one unit and you can build the left and the right part. So you add a Weyl fermion, and by convention we call it a right-handed neutrino. So we add this guy. What happens? Let me just show you, and then with these pictures we can also discuss a bit. Here is the limit where M4 tilde, which is this product here. I will reverse this. I can vary this, okay? In these plots I'm varying. I took 4 benchmarks for this, which is the magnitude of the vector. If this vector is very small in the limit that this mass is very light, you get the IO. I'm considering also IO for all these plots, inverted ordering. You get exactly what you have in the standard case. But if you have it, for instance, at a certain value which is comparable with the size of the other largest vector, they can cancel. Depending, of course, on the phases they need to align, but you can have cancellations even for inverted ordering. So this is just to show you that we don't know the full picture. We can always have potential processes to probe lepton number violation, like neutrino stable beta decay. But since we don't know the full theory, it could vanish. If you say, my full theory is just, I don't have sterile neutrinos, I don't have anything else, then you could, and I have inverted ordering, then you could say neutrinos are Dirac. But you are assuming too much. If you have some change to your theory, even inverted ordering could give you a canceling signal. Okay. Questions? Yeah. So if you add a sterile, even with modest couplings, it can change a lot your range. For instance, if it's very large, it will dominate, no? If it's, you see there is a difference between this order of magnitude and the other ranges. So when people present you this diagram, keep always in mind this is the standard picture, but we don't know if it's true the standard picture. Although I would not put my money on sterile neutrinos. Okay, what if we had a heavy sterile neutrino? Is this the question you're going to ask? No, okay, maybe we have other contributions which are not a new neutrino. Maybe you have some scalars, and you can also get modifications to the standard rate. It's not necessarily a neutrino. Yes. Yes, if you believe in the type 1 seesaw. If you believe in the type 2, you don't need extra fields, extra fermions, right? I mean for the sterile. In inverse seesaw, you have, for instance, as Claudio was showing, something at keV scale. Yeah. Yes, it will affect this. Of the inverse seesaw, this. Yes. Yes, these are something which will appear when we consider a mass generation mechanism. But you see that if it's very light, you don't have light neutrino. You are not doing a seesaw. Yeah. So people usually invoke steriles for other phenomenological reasons, like short baseline anomalies, even though it's not very satisfactory solution, but it's something else, but it's similar in that sense that they are right-handed, sterile, so gauge singlets, and they will affect this if they are sufficiently light. If they are very heavy, even I'm putting here M4 to 10 GeV, but even if we consider them now instead standard model with the usual neutrinos, massive neutrinos, and a very heavy guy that could be 10 to the 10 GeV, what would happen to M beta beta? Would it explode because of this going very high? But am I applying the correct formula? Yes, this is the expectation. It should decouple, right? So what really happens? Diagrammatically, you can see this. I will draw again the diagram. So if we exchange light neutrinos or the sterile, which is light enough, the computation is as Claudia did. If it's heavy, you recall there is this propagator, no? And actually this part Claudia showed with projectors that was not there. But we were taking the limit where this was very small. Now it's the opposite. So there is a suppression. So if you are in a region where you're sterile, your new fields are very heavy, instead of having it like this, you will get something which is like this. So you are safe. It will not affect neutrino stable beta decay. Okay. If it's in an intermediate range, you maybe have to deal with the full propagator and do the computation. It's not so trivial. But in these limits, you see, light neutrinos gets this very simple formula we've been discussing since the beginning of the lecture. And if it's a heavy guy, the contribution will be suppressed by its mass. Is this clear? Sorry? Actually, here, heavier light, what I mean is with respect to the scale that you were also, Luigi wrote this morning, which is a scale of the usual transverse momenta that is being transferred in this diagram. So the scale of this, I'm P, which here is P, is this momentum here. If M is very light, we can do what he called the closure approximation, which is what you'll find in books. If it's very large, it's integrating out, let's say, this particle. Yes. Yes, it's essentially, let's say, this is more or less 200 MeV, which is basically inverse Fermi in natural units. It's if you are dealing with nuclear distances and you do this computation of units, this is the kind of moment you get. Okay. Questions or comments? Can we move on to the black box theorem? All right. So 3.4, we'll try to discuss this together, is the black box theorem, which was found many years ago to argue that if you find neutrino stable beta decay, even if your theory does not give a mass to neutrinos, you cannot escape giving a Majorana mass to neutrinos. Okay, this is a kind of, we are trapped. If we find neutrino stable beta decay, we have learned something about neutrinos. We have learned that they are Majorana particles. Under very general conditions, this is true. Yes, even if you take standard model, okay, they could be no, they have to have a mass. So, but the point is that it's due to if you find the 0 new beta beta in the laboratory, the strength of this signal will generate a mass, a Majorana mass to your neutrinos. We will see it now with the diagram. So how does the diagram look for neutrino stable beta decay? We don't know exactly how it looks inside, no, but there is something happen. If we see neutrino stable beta decay in the laboratory, this operator exists. Something which takes an electron, okay? Actually, which emits 2 electrons. Okay, let's do the arrows like emits, and takes a D and goes to an up, right? Because there is a D quark and an up quark twice for each nuclei, right? For each nucleus. So if we see neutrino stable beta decay in the laboratory, it means this thing is not 0. We don't know what it is. It could be just a standard exchange. It could be exchange with steriles. It could be something very strange which has nothing to do with the generation of neutrino masses. This is a very important point which Claudia tried to stress. The origin of lepton number violation and of neutrino masses, they can be completely independent and separate. Here we are looking at lepton number violating processes. What Schrechter and Valle have shown is that this will affect a bit also the neutrino masses. How? So how can we get neutrinos? This you discussed in class. How can we, in the diagram, get from this diagram to a diagram with neutrino masses? Yeah, loop of W's. Okay, W here. So I get my neutrino, no? And I do the same on this side. Okay? Now I don't want many particles to come out. If I look far away enough, what do you see here? If you close everything somehow inside here, okay, this is what they call the black box. But this bigger box here, if somehow all the fermion lines close and no fields come out, what is this diagram? It's a Majorana mass term. So for the neutrinos, you see the arrows are going in these directions. They are not like a Dirac term, which would be something like this, no? Diagrammatically, I mean, it doesn't, you don't need to understand this in detail if you never worked with the propagators and so on. It's just that if the arrows keep going in the same direction, you have a Dirac mass term. If they go together or go away, it's a Majorana mass term. The whole point of Schrechter and Weil was to show, but we can close this diagram because if you have an up and a down, okay, they can transform to each other with a W. This is what Claudia drew, no? So this means we expect a contribution. Sometimes it's drawn like this. Okay, this depends on conventions. Here it's going in, but it's nu E bar, so this is like nu E going out. You can, the point is, if the black box is not 0, you get, in general, Majorana mass term for the neutrinos. Now, let's, 2 questions. First, what is the dimension of this operator? It's coupling 6 fermions. What is the dimension, mass dimension of a fermion? 3/2. So it's coupling 6 fermions. Okay, it's E E D D U U. 3/2 times 6, 9. So if I want to write this in my Lagrangian, I put this operator of dimension 9, and it should be minus 5. So I need to put a scale here, which is 5. Does this make sense with this diagram? I mean, this is a diagram for neutronless level beta decay, no? This is my black box. Suppose inside this black box, this round black box, round box, I have this process here that we've been talking about a lot. Do you see this lambda, these 5 mass scales? Where are they? Yes? So 2 from the W's, right? Sorry, I misspoke. Let's imagine, I mean, this operator is an operator of dimension 9. I want to see how I could get it by integrating out fields. So let's suppose I have this exchange of a heavy guy. All guys should be heavy here. And I was asking, does this and this somehow match? And the reasoning is you have a suppression from 1 over mw squared from this one, from this propagator another, and then a suppression by the right-handed neutrino. So just to say that if your fields going here are very heavy, you can reduce all this to a point, which is that point here, the black box. And okay, it makes sense. If the fields are light, like exchange of light neutrinos, you'll not get this suppression. It's something that is not integrated out. It's not an effective operator. But if the contribution is something that you can integrate out, then in a SMEF description, in an effective field theory description of the standard model, your Lagrangian will contain this operator. And we can estimate this. So there is this operator, which is entering here. This black box is this operator of dimension 9. Can you give me an estimate for this? If I tell you, okay, O, the coefficient of O, so this coefficient 1 over lambda 5, sorry, let me call it C. If I tell you that this guy, C over lambda 5, is, let's say, GF square over mass of the proton, how would we go about estimating the Majorana mass for the neutrinos from that for-loop diagram? The task now is to estimate the Majorana mass for neutrinos from this for-loop diagram. What should I write? Contribution to the neutrino mass. Of course, we're not going to compute in 3 minutes the for-loop diagram. They're going to estimate it. So from the lectures, what did you learn? I'm computing that guy there. What do you have there? Yes, but how large is it? If if I tell you that this coefficient here, this C over lambdas 5, the thing that enters the box is GF square over MP, then it appears in the amplitude, no? In the amplitude of this diagram, what else? There are 4 loops. 4. So already from the lectures you think this will give me a very tiny number with respect to neutrino masses. They are light, but they're not that light. And is this correct dimensionally? By the way, let's see, we have propagators there, no? For sure we have the mass of the W to the 4. What am I saying wrong? Loop factor. Maybe I gave you this number wrong. No, this is okay. Dimensions wise is okay. So what mass scales are missing here from the problem? I mean, in the end, I can tell you that the important factor is really the loop suppression because the masses of the fermions going around are important. So to do this estimate, you will use ME, MD, and MU squared. Okay? And actually, I think I wrote something wrong, but I think in the end, this will be the correct estimate because of GF there, already including the W's. Okay, so bottom line is, if you estimate this, how much do we get? Well, because I probably made a mistake when I give you this coefficient. Yeah, now I'm not seeing what is the mistake I made precisely. This is order 5. There should be 1 over MW. Yeah, sorry about this. The computation is done explicitly in a paper, and I tried to take the juice out, but maybe I made a sequence of mistakes. So it's not clear to me exactly why the W doesn't factor here. Yes. Yes, probably because they do this with some coefficients which are dimensionless. And to get there, I don't recall how they do it. Yes, this is dimensionally correct. No, it's missing something. What is the dimension of this? It's mass, no? So it's correct. It's 1 over mass squared. GF is like 1 over mw squared. So this is essentially 1 over 200 to the 4th. This guy is 1 GeV. This guy is 10 to the minus 5 GeV squared. Sorry, minus 2 squared. This is 0.5 MeV squared. Mass of the down and mass of the up. There are also a few MEVs, no? So essentially these are MEV to the, which is GeV 10 to the minus 3 GeV. Okay. So 10 to the minus 18. Yes. 10 to the minus 32, no? 32, no, wait, but then there is a factor. We get 35 JeV, which in electron volt, this is 10 to the minus 26, no? Okay. So as Claudia was saying, this is much, 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 much smaller than what you are seeing for mass square differences. The precise estimate gives you something like 510 to the minus 28, even smaller, okay? But already this loop factor should be an indication, as Claudia said, that we don't usually go below 3 loops because you will never get neutrino masses which are of the order of M2, M3, or M1 that we are finding. So what do we see here? What can we conclude? If there is any lepton number violation, it's very small. Not necessarily. If there is any lepton number violation, I'm assuming I find it, and it's largish. I mean, right? I'm assuming I'm finding it because I'm putting this different from 0, and it can be large. But so what do we find? What is the correct conclusion? From this, right? And perfect, yes. So neutrinos cannot just get a mass from this diagram, right? It's too small. And so there should be some other contribution to give the delta m squares we see in oscillations. But are neutrinos Dirac or Majorana? Majorana. Because even if it's a very academic thing, a bit, it's not like the mass is part Majorana, part Dirac, but lepton number is violated in nature, and this will give you a Majorana mass for the neutrinos. Contribution, as your colleague is saying, it needs to be supplemented by some other contribution, which could be completely Dirac in origin. But neutrinos in the end will fundamentally be Majorana because there is at least this contamination there, even if they behave as Dirac everywhere else. Okay. Yes, because it's they will have a mass term which breaks every U1 symmetry. So lepton number is broken, and there is a mass term for the neutrinos which also breaks it because of this. But then, okay, maybe it's a bit academic because it doesn't tell you much more. Why do I care if they are 10 to the minus 26 of the mass, gives them Majorana character, but otherwise they behave as Dirac. Still, you answer that there is lepton violation. Well, you knew that there was lepton violation in nature, lepton number violation, so you know that neutrinos are Majorana particles fundamentally. And Ettore Majorana was right to do his theory. It was not completely crazy. Okay. Other questions? Okay, if not, the last exercise will take us the rest of the class. And here I would really like, I mean, I see some computers, so it would be nice. You don't need to use the computer, but it's easier. Is to consider this explicit example for a neutrino mass matrix, okay, where it's 5x, x is 10 to the minus 4, 0.05, 0. So it's a symmetric matrix, which has a very nice structure. And I want you to calculate the matrix you knew that diagonalizes it and the neutrino mass square differences. Okay. So this, now I leave you to do it alone or do it with people around you. This is really a computation exercise. I will just write down some few things that can help you. But you should already have everything you need in your tools. You should have all the tools. This is all you need. It's the convention. Sorry? I don't know if I did. But what is the rotation matrix? Ah, I see.
This is exactly the same
Okay, very well.
matrix you give us.
So you can do it without a computer.
Exactly.
But do it. I want numbers. I don't know, you have to ask them. No, it's okay.
About the time.
I, half an hour, I'd say.
Half an hour still, so we do lunch at 1. I will tell the
Okay.
ladies. And then when do you ask someone?
No, no. So I will do it now, actually. Thank you for reminding me. Yes. So in the meantime, 5 of you will present today. Are you all here? Show of hands. Who is presenting today? 1, 2, 3, 4, 5. Okay, perfect. You should, do you have your talks in slides, PDF? No, but I would suggest that you upload, if it's all PDF, to the folder.
You all have the link to the shared folder of the school with the material that Joao just gave you. And so please do the upload, which makes it for us much easier to change the slides. Otherwise, you would have changed computer. And the point is also, actually, Maura, Giuseppe, and Davide would like to connect to the Zoom so that they also have a chance to listen to your presentations, because they unfortunately cannot be here in person. So then it's better if you have this on one computer only. And is this all okay for you to have the PDF then uploaded? So you all have a PDF for the slides, or you have
Something else, like PowerPoint, Keynote.
If you have PowerPoint, it should also be working. We asked Alessio.
It seems they all have PDF. We are clear. As you prefer, upload the one you want.
Yeah, I mean, that shouldn't be. The only problem is Keynote. If you insist on having the Keynote file, then
Sometimes with PowerPoint, the fonts can be problematic if you use something non-standard.
so then I just disappear. You don't. When shall we
They're
say
busy
the
with the
lunch?
exercise.
Okay, good. The lunch we do then until 2:15, and then we start at 2:15 in the cultural place.
Okay. Okay, when we close. Thanks.
So then I disappear again.
Go, go. So I want you know, and I want the masses. This is not just a copy of the other exercise, okay? We will see something very curious in this example. How are you computing the masses? The eigenvalues of m nu? Yes. First pitfall. Don't forget to use the Hermitian combination. Does anyone have numbers? Or I give you a bit more time? One of the eigenvalues is? It should be trivial because this matrix is by blocks, okay? So it is 2.5 times 10 to the minus 4. Really? But they will mix, there is a mixing there. And when you diagonalize the 1-2 block, there will be a splitting. So it will not be 2.5 times 10 to the minus 4 in the upper block. People with computers, do you find, if not yet the eigenvectors, which is maybe more tricky, the other two eigenvalues? Okay, so one of the columns, so the columns I write, one of them is also very easy. This is the eigenvector, of course, that corresponds to this eigenvalue, but the other two are the interesting ones. The other eigenvalue is? No? No? Try again, because these are all three different eigenvalues. And don't forget that there is the square root, of course. Yeah, maybe this is the problem. There is a square root, no? If you are computing the eigenvalues of m dagger m, then if you want the masses, you have to take a square root. Where in the eigenvectors? It's not true. Okay. No, how much order of magnitudes in EV? 10 to the minus 2, okay. You see, so the theorist, I mean, everyone is computing things, but the theorist thinks, okay, I just estimated by. I mean, if you don't have a computer, Matteo, I mean, you cannot complain that the exercise is trivial if no one gives me numbers. Yes. But numerically, I mean, I see a lot of computers, so in good faith, I'm assuming that all of you are using your favorite program to. Yes, this is what he's doing, but he also doesn't give me numbers. Oh, okay, very good.
Ah, okay. I don't finish this. But just assume these two are small. I mean,
No, no,
some are smaller. No, you can just take it very easy. Oh, no.
you can do a Taylor, yes, but
That should be very straightforward.
the later I have numbers, the later we go to lunch. I mean, my hands are tied. Do we get some minutes? Oh, this is a rush between analytics and numerics. It's a race. Guys with computers, any progress? Yeah. It's okay. It's okay because no, wait a moment. You get the negative values. You're already very far ahead. No, you did the eigenvalues, the diagonalization. Okay, so you guys can already think what to do to get the positive eigenvalues if you want to go ahead. But if you diagonalize the m dagger or m dagger m, you should get all positive, real, and then take the square roots. Th- then if you want to, because you should not diagonalize m nu directly, right? In the sense that this is unitary, but this is not the inverse of a unitary matrix, like in linear algebra. So the trick is you do something like m nu conjugate m nu, right? This matrix H, if you look at here, you have u dagger nu, and this is normal Hermitian, something diagonalizable. You will find these three guys in some order. And if you take the square roots, you will immediately get the masses. But this is not the end of the story. You asked ChatGPT. I'm curious. So, ChatGPT versus analytics versus numerics.
Not that it is it's cop out, but 0.0005, 0.00035.
No,
No, he's wrong.
ChatGPT is wrong. As long as they're not degenerates. I mean, numerically, this one should come out for sure. Because really, this is completely decoupled. One point. 10 to the power minus 8. Really? Let's see. Yes. Aha, this is the problem. No, but this. Ah, okay, okay. Ah, and you're. Mhm. Okay. You should have eigenvalues of m nu, dagger. Not just transpose, but also conjugate. Ah, but it's real. It's real. Oh, sorry. But in general, it should. And you should not have the PMNS there. I mean, it will not do anything. So it's a. You should not have it there. Yeah, not at all. I mean, it's a matrix, which is this product, or the in the other order, which you want to diagonalize. So it's just to answer him. You have this matrix. You want its eigenvalues, and its eigenvectors will be the column of u nu. You don't put u nu. You don't know u nu. You want u nu. This is something else we want.
Uma coisa errada, porque deu negativo 1
Mas eigenvalues de quem?
dessa matriz aqui.
Não, mas é que. Okay, so clearly, yeah. Please, guys, the eigenvalues should be of this guy, and you will get the masses squared, and you take the square root. Some question? In this case, m nu star is equal to m nu. Yes. What? It's not general. Ah, no, but don't worry. X will not be imaginary. you can, X is real. Ah, very nice. Did you find the masses? If you have the mass square difference? Yes. Just output EV. Okay. We have one person who gave us the correct eigenvalues. But for those of you getting something 10 to the minus 8, this is because you are forgetting the square root. Then you take the square root, this should appear. Okay? The other two are very similar, but as the theoreticians were finding out, but they are not degenerate. And Mirko found it numerically. You should also get it somehow, even in your expansion. They are very close together. They are close to this off-diagonal value, 0.05 electron volt, but they are like this. So, yeah, okay, so you see these two values. Within, yes. We have inverted ordering necessarily, in the sense that we have a light guy and two very degenerate guys, almost degenerate guys, but which are heavier than the light guy with a large separation. So we have a situation which looks like this in the masses. And this is inverted ordering by convention, where the mass splitting of the first of the ones who are close together are M1 and M2, okay? And the other one is M3. And this is very important because now if you want to find u nu, it should obey this, as Claudia told you, with some insistence, but at the time maybe it was a bit cryptic. You need to make sure that you get this ordering. This is also convention. M3 is the lightest, and this guy should be smaller than the other two. So first thing we just recognized is we have this, and if we want to find u nu, we need to bring it to this form. So this will tell you exactly how to order the eigenvectors. Does anyone have the eigenvectors in this problem? The eigenvectors that correspond to this 49, up 496, yes, and 504. Eigenvectors. Minus? Okay. 1, 0. 0, okay. See, yes. So, first question, are these guys normalized? No, okay, so can you normalize them? You see that you basically divide by square root of 2, okay? So this will be approximately minus 0.7, right? Minus 1 over square root of 2, and this will be plus 7. I mean, this is approximate, okay? And then you have to find out. You're very lucky because the smallest one is already in the third position. So what kind of matrix do you expect this to be? I mean, its columns are these guys. Yes, we have to organize these columns to get this guy, right? The correct ordering, if you find it numerically, you can test. It's this thing. This is the correct order. So people with numerics, try this. What happens if you apply this U to this matrix using this equation? Can you tell me? This will take some minutes. So the M you have there, U, I just told you, we found out together, it turns out to be this. Sorry, maybe I have a minus sign. There is a difference of signs for some reason. And you can multiply it by a sign. It's still an eigenvector. Okay. The point is that these signs are different. You can write this as should be very close to 45 degrees. It's actually 45.1 degrees. Okay, so precisely. Right. It's really basically maximal mixing because you have to diagonalize, so you really have to do the full rotation of the matrix. Yeah. Now, people who have the numerics or even just want to use this, I mean, does it work if I use this U nu to get this? What do you get? So here, let me call it C minus S. So this will be M3 directly. And this is this 5x 0.05. What do we get here if you do this computation? Is it the correct one? I mean, what do you get when you apply this here? Do the U transpose M nu U. Any takers? Do you know what happens? Is this correct? Do you think this is correct? It's not correct. But not because we made a mistake in the big part of computing eigenvectors and eigenvalues. Don't worry about that. Just if you do this, what do you get? Did you compute this? Wait, okay. And now it's easy. So what do you get for the first eigenvalue? Okay. Okay, so you get minus, yes, minus 0.048. And here you get? You should get 504. And here you should get 59. Okay, okay, but these numbers there and this small number there is 2.5. Okay, 10 to the minus 5. Yeah, this is the problem, no? So what does this mean? What is the correct union? What do I have to multiply? Yeah, so if here I put minus 1, it will cancel any minus 1 that I put here because they will cancel. And you don't destroy the sign. So what should I put to get rid of this horrible sign? Okay, so if you put I on both sides, plus or minus I, doesn't matter, you will get the correct U So the correct U is this with an I here. Okay, this is quite important. We will see exactly how important this is in the next step. I want you now to vote. So this is the correct matrix. I want you now to vote on the answer to this question. Can this matrix be part of a phenomenologically viable model for the lepton sector? And Mirko already computed the mass square differences. Do you remember how big they were? Mm-hmm. Electron volts squared. Does this sound good to you guys? Yeah. The mass square difference of solar, 7.5, 10 to the minus 5 electron volts square. And if you compute the atmospheric, you also get something which is okay, 2.5 times 10 to the minus. So there is no objection from mass square differences. But can it be, and this is a trick question, can it be part of a phenomenologically viable model for the leptons? Who says yes? Who says no? People say no. You say I don't care, and you don't know. Okay. No, it is because so the columns are have norm 1, no, and the I is okay because when you compute the unitarity condition, it will cancel. So it could be. This is okay. You say it could be because I mean, if the lepton sector is diagonal, can it be? It can't because I mean, where is theta 2, 3, theta 1, 3? But this is just asking for a complete lepton model. Can this be part of it? Yes. it has the delta m squares, and as long as the rotation from the charged leptons gives you what you need phenomenologically, because recall, U, P, M, and S is not this guy. In general, there is this rotation here. Okay? So, can you estimate M beta beta in this case? I mean, order of magnitude? If it's okay, so let's assume that the angles are okay now. This UL gives us something that makes this acceptable. What do you need to use to assume? No, but if you assume the wrong phenomenological model, we'll do this in a second. But if it's right, I mean, just thinking about the diagram, where are we at the diagram of neutrino stable beta decay? We're in inverted ordering, right? This is the first thing we concluded, that we are inverted ordering, so we expect to be in that band, and if you look at the plot, you really have a lightest mass around here, so you are here. If you want to compute the Mariner phases, you could, but order of magnitude, you expect this. Okay, so to close, what about this limit? This is the last exercise. This limit x goes to 0. And there is no UL. So if UL is 1 identity, what is U nu in this limit? It's a terrible PMNS, but what we get? If this perturbation goes away, this is no longer approximately just 45 degrees, okay? It's exactly, okay? Does it make sense? No, I mean, we are going towards a matrix which is something like a block width of diagonals. We need this 45-degree mixing. And if this x is 0, this is enough to diagonalize. Oops, sorry. Yes. Exactly, they will be degenerate. So already there, phenomenologically, no. Then if I say that UL is identity, completely no. Because you need all the other angles. So this would be the PMNS. Okay? This is the 45 degrees. It's really 1 over square root of 2. And there is the I. It's always there. And now I want you to, by yourselves, compute the M beta beta. (0.05). Okay, one idea is 0.05. Okay, let's put. You say it's 0, you're very bold. Approximately 0? Okay, exactly 0? I can give you that. What else? Ideas, can you compute it? Don't forget, if UL is 1, this is not phenomenologically viable, but this is the PMNS. Okay, so. Yes. 0.05, so. Pam, pam, para. So. Yeah, let's see what it is, okay? Let's see it. Help me. I mean, what is cosine theta 1, 2? It's staring you in the face. No, I mean, just look at it. Theta is 45 degrees, so cosine is 1 over root 2. Sine? The same, no? Cosine is, sorry, we don't even need the rest, actually. M3? M1? 0.5, I mean, you don't have x anymore. And M2? So let's call this M. Okay, the third term goes away, no? Oop, I'm going down. What are the Majorana phases? Pi over? C13 is 1, okay, but it's not important. This is 1/2, this is 1/2. This is eta 1 and eta 2. How much is eta 2? Yes, we are in the basis of diagonal charge leptons, so you can see it. Okay. Okay, so it vanishes. But can you explain why it vanishes? With words, not with numbers, because we computed it, we find 0. But where are oscillations? I mean, we're talking about m beta beta, no? No, they can have masses, just that the masses are degenerate. But they could have degenerate masses and still be Majorana particles, which give you a contribution to m beta beta. This is not an objection. I mean, yes, I know that computing it, I get 0 if you do it this way or that. But why m beta beta is exactly 0, not just approximately 0, not because I tune some parameters. Okay, but this is correct. We cannot have violation of lepton number. So this would be a very good reason. If lepton number is conserved, this is a very good reason to say it's exactly 0. It's conserved. Why is lepton number conserved? Let's look at the third neutrino. I mean, in this limit, what is its mass? 0. What does this mean? I mean, there is no mass term. So you don't have the usual problem with Majorana mass terms, where you try to do this lepton number rephasing and then get a clash and exponential of twice the phase. No, there is no mass term to bother you, so there is no mass term for M3 that breaks lepton number. So the third neutrino is not our problem because it has 0 mass. If it did not have 0 mass, and we can also see it from the computation, it would give something in general because it would be a Majorana particle. But with 0 mass, it's not Majorana nor Dirac. It has no mass. You can see it. It's a massless fermion. No, the story does not end here. So this is part of the reason, yeah. So part of the reason why lepton number is conserved is because one of them is massless. But still you have to check the other two because in general, you're right. If they are there, they have masses, can be Marana masses. But this is actually, here something has happened which was mentioned in the lectures. Where you think you have 3 Marana fermions, but you don't have 3 Marana fermions. It's not that. Almost. So it's right. It's a good. Yeah. It's important that they have the same mass. Sure, in the oscillations, which is completely. It's not okay with phenomenology, but it will not help us understand why lepton number, because oscillations will conserve lepton number as we've seen.
So how would you write the mass matrix for these two states? If you have the one and
Actually, they did it. They even saw what was the Marana phase. Xi was giving an eye. So okay, let you go to lunch with this funny limit. No, the two Marana fermions having these opposite CP parity, so this specific difference of Marana phases and the same mass, they can be combined, as Claudia told you, into a Dirac fermion. Okay, it means that when you transform, you can find a Dirac fermion with only one phase rotation. This is a lepton number, whose mass term will not break it. Mass term will remain invariant under this lepton number. Yes, you can construct. Yes. So this was an old idea by, I think, Knopinski, Mahmoud, and collaborators. But they asked, can the neutrinos we observe in nature be Dirac like this? That one is the part and the other is the other part, and they combine. And the answer is no, because it would need degeneracy of masses, and we know that there are no degenerate active neutrinos. Okay. Okay. So you just computed something which I think is curious, but maybe you're just very hungry. So I thank you, and let's go for lunch.